Hi Hires, we're looking at control of metabolic pathways in metabolism and survival. So if we want to control a pathway, what we really need to look at is the enzymes. So enzymes, you should know, lower the activation energy that you require for a particular reaction to occur. Okay, the things that you would see generally for a catalyst is they speed up reaction, they are not used up by the reaction, and they lower the energy required. So what we have here is a pathway on this particular reaction, which is just respiration. The red is showing it without an enzyme and the blue is when you have it with. If you have a lowered activation energy, you can run things at a lower temperature, which means that we can stay alive. Enzymes work by induced fit. Now this is a step up from what you had at NAT5. At NAT5 we had the idea of lock and key. This is the next level up. So what we mean by that is that the substrate, which has a high affinity, that means it likes being near that enzyme, will join at the active site. Now that's not any change apart from this term high affinity. But as it joins, it binds to it, and that means that it's going to change the bonding inside the enzyme, which means it changes the shape of the enzyme round about it. And it now fits even better than when it started to join in. And as it does that, it actually makes the enzyme catalyze the reaction. And that changes the substrate to the product. Now what's important now about the product is it's different, which means the product has a low affinity and therefore leaves the enzyme. It's a very neat system. It effectively means that the substrate causes its own destruction or production to something else. So we have the substrate binds to the enzyme at the active site, changes the shape of the enzyme to better fit it, that's induced fit. The reaction proceeds with a lot less energy than you would normally require because everything is being held in the correct orientation. Alters the substrate to product. Product no longer binds because it's got low affinity, so it's released. And then the enzyme is free all over again to start this. Here's a nice little example of this one. This is hexakinase, which alters glucose, and the little red blob is glucose, and you can see it's coming into the hexakinase, and when it joins the hexakinase you can see the shape of the active site is actually altered. So here we've got a kind of open section, and when the glucose is attached, that section has been folded round it. So we need to map what's going on, and to map it we need to track the enzyme activity. And we're either going to look at decreasing the substrates or increasing the products. That's obvious. There's lots of things we could do. So we could look at gas production, we could look at pHs, we could look at colour, anything which will give us a range of measurements, and that might decide whether we go for the decrease in the substrates or the increase in the products. You need something that you can actually measure. What you then do is take the rate at the start of the reaction and then you plot it over lots of different measurements, and then you plot that on a graph. So if you plot all this information, you can produce a curve, and this would be a very common curve. This is your concentration of substrate versus your initial rate of reaction. So this was lots and lots of experiments. So they did an experiment at this substrate concentration, found out what rate that gave and plotted it, and then joined them all up. Okay, and you've got some new numbers on here. At the top we have something called Vm or Vmax, and what we mean by that is the point at which even increasing the substrate, so if we keep on going along here adding more substrate, we're not bumping up the velocity anymore. So this is the maximum velocity that we can get for that concentration of enzyme. If we take half of that and work out, going across the way and down, how much substrate was needed to get half of the maximum velocity, we get another new number for you, the Michaelis Constant. And what that is how much affinity the enzyme has for the substrate. So a low Km, so if we were down, say, here for our Km, okay, so here's our Km down here, sorry, something going on with my pen. And so if that gave us half of the maximum velocity, you're like, actually that curve would have been much, much steeper. Now what that tells you is that this would be an extremely quick binding. Now that can be really important for things like toxins. If you have a chemical which has a really high affinity, so a very low Km, then it will attach to the enzyme very, very fast. If it has a very high Km, then you're like, well, then it's taking a while for it to get, so if we took it along like this, we would say, okay, there's half. That's what the concentration has to be at before I can get to half of the maximum velocity. So it's a really useful and important measurement to do with enzymes. Okay, temperature you should be really familiar with. It is the curve that you've had since third year, asymmetric. At low temperatures, low activity, hit an optimum, hit a point where you denature, and then the whole activity just drops down like a stone. Okay, and you should be able to talk about that reasonably well. So as you increase temperature, you increase enzyme activity because everything's moving around a bit more. Optimum point, and then you've damaged the structure of the enzyme, so denatured, and that's it. The shape will be the same, but the actual optimum will be different for different organisms. So here are some examples. We would put ourselves in at the mesophiles, which basically means normal or medium, and then we've got our low, we've got our highs, we've got our super highs. So if we want to control our enzyme reactions, since they're really complicated, lots and lots of different things, we could pick and choose what substrates are there, and that can drive the reaction. We can control the enzyme activity through inhibition. Now that's the next bit, and that's really important. So we can slow down enzyme activity using chemicals called inhibitors. And kind of obvious, we're inhibiting activity two different ways. A competitive inhibitor is in competition for the active site. Again, I think that makes sense. Okay, so it's competing for the active site. If there's enough of it, it will just block the substrate from getting in. A non-competitive inhibitor is a little bit different. What it does is bind somewhere else to the enzyme and changes the shape of the enzyme. So if it changes the shape of the active site, then nothing can fit in there that normally could. So if we look back at our curve that we have for normal substrate and rate of enzyme activity, we get two different curve changes for the competitive inhibitor and the non-competitive. So the competitive inhibitor is decreasing Vmax. Okay, the non-competitive inhibitor is not decreasing Vmax, but it is changing how long it takes to get there. So what you're actually doing with the competitive, if I can just take a line across, okay, here's our competitive. So this has now changed its Vmax from here to here. Drop it to a half, however, and bring it across and bring it down, it's actually got the same Km. Okay, if I take the non-competitive though, Vmax is the same, but if I take my half is way over here, so when I take it down, it's totally shifted the affinity of the substrate. A bit more detail on that to explain what's going on. So in the competitive, we lower Vmax because every time the active site is blocked, you can't run the reaction, so overall we're going to slow everything down. There's no effect on Km because you've not changed the active site, so it's still got the same affinity for that particular substrate, it's just not getting there as often. Okay, on the non-competitive, no effect on Vmax because you haven't changed the activity of the enzyme, it's not slower, there's just less of them that are actually able to do their job. And the Km is going to go up because now we've changed some of the active sites, it will take a lot more substrate to get them kicking in. So one of the biggest issues with enzyme activity is if you stop it when you shouldn't, and that would be a toxin. So the level of toxicity, so how much damage it does, depends on quite a lot of factors like absorption and various levels of things to do with that, but also the affinity that the toxin has for the enzyme. So basically the lower the Km, the worse it is, because the quicker it attaches to enzymes, the more damage it's going to do. And then also the mechanism that it has, is it competitive or non-competitive? Now that matters a lot in terms of the potential for getting over a toxin damage. So if you've got inhibition and it's competitive, then you can basically outcompete it just by increasing the concentration of the substrate. Because the more substrate you have relative to the inhibitor, the more chance the substrate has of getting to the active site. So you can overcome competitive inhibition by increasing the concentration of the substrate. That's an important point. That's just an extra. If it's non-competitive, that doesn't work at all, because even if you flood the whole system with huge concentrations of the substrate, the point is that the enzyme's active site has been changed in shape, so having more substrate there does not help. Lastly, we want to look at feedback inhibition. This is a form of negative feedback, one of the neatest ones that you're going to find. Basically, what happens is once your final product has reached a particular critical concentration, it will just slow down its own production by inhibiting the enzyme earlier back in the pathway. It doesn't have to be the first one, it could be down the road. But what it's actually doing is just blocking making more of it. And then once it's used up and it's at a low level, then it will stop its inhibition and more of it will be produced, and then it will slow it down. It's a very, very neat system. And that's us on this.